Okay.
Okay. Very good. So thanks a lot. And so yeah, I'll discuss this last couple of papers here down here that I wrote in collaboration with Andrea Banfi and Frederick Dreyer last year, where we addressed the calculation of so-called non-global observables at next to leading log order. So well, first of all, feel free to interrupt me at any point if for any clarifications. So let's start from a brief introduction and see why these observables are so interesting in collider physics and what we want to understand. There are several reasons. First of all, so what are non-global observables? These are quantities that by definition measure the radiation differently in different angular patches of the phase space. This non-democratic treatment of radiation results in a certain specific type of imbalance between real and virtual correction. That in turn results in the appearance of logarithms of the ratio of the energy flow in the different angular regions that contribute to the observable, that in the perturbative expansion of the latter. So in some cases, this can be treated with normal fixed order perturbation theory, but in extreme kinematic scenarios, these logarithms become large, and therefore we need to reorganize the perturbative expansion in order to resum them at all orders. So there are many examples in collider physics. One is, of course, the use of jets. One is like the measurement of the ungroomed jet mass, or the application of rapidity cuts on jets, as well as isolation criteria on photons, for instance. All of these receive a contribution from global corrections that I'll describe, but as well as the application of jet vetos that, for instance, are used to classify events according to their jet multiplicity. That is a very common thing, for instance, in jet physics, where one classifies the events into 0 and 1, exclusive to jets, and so on, to single out, firstly, different production modes, as well as to increase the signal over background ratio, and therefore increase this experimental sensitivity. A second reason why these are important is the development of Barton shower algorithms. In recent years, we've made a lot of progress in understanding how to build next to leading log algorithms. These new algorithms can be tested with very high numerical precision against more analytical resummations. Now, a crucial thing to understand here is that in a next to leading log calculation that starts with double logarithms, a non-global observable would, in general, show up at the single logarithmic. Global logs would show up at the single logarithmic level. That means that non-global logarithms in a double logarithmic observables are a next to leading log contribution. So in general, to build a next to leading log Barton shower, one needs to understand how to resum non-global logs at leading log, and how to incorporate this resummation consistently in a Monte Carlo shower architecture. So this is interesting, but in the long run, we need to push this accuracy to next to leading log to really reach the few percent precision that is demanded by the LHC, as well as I mentioned, future colliders. And doing this is a whole new problem, and it's a very tough task, in fact. But one of the requirements is understanding and developing the theory for the resummation of non-global observables to next to leading log that, in the context of a generic observable in the shower, will contribute to it would be a building pillar of a next to leading log Barton shower algorithm. A final, more formal reason why these observables are interesting for us is that the dynamics that describes the evolution of soft gluons at wide angles with respect to the Haas scattering process that is behind the existence of non-global observables is connected very intimately with the high energy behavior of scattering amplitudes that is described by the so-called Jim-Walk equation. And the two apparently very different kinematical regimes can be connected by a very elegant stereographic projection that basically allows us to look at the two problems as the dual of each other, which means that if a progress is made theoretically in the understanding of one problem, this can be ported within some conditions into the other problem, which is extremely interesting. So,
excuse me, can I just ask something? So I know that in pan scales, several of you developing a next to leading log initial state shower. And I was a bit curious that the previous slide that you have, does that mean that you also have to somehow solve the Jim walk equation at that accuracy, or?
No, absolutely not. So there is a relation between the equation that governs the evolution of non-global logarithms, the BMS equation that I will introduce shortly, and the corresponding BK or equation, or the Jim walk equation in certain limits. But the two are really different problems, right? So it doesn't mean that if you implement the resummation of non-global logarithms in the shower, then that shower will also accurately describe out of the box the small x limit of a scattering amplitude. No, this is although formally there is a connection between the two equations, there are deep differences in the kinematics. So if you implement this BMS equation in a shower Monte Carlo, that will be used to calculate non-global logarithms, but it cannot be used to tackle the Jim walk equation, at least in the simplest form, right? And my guess is that it is highly non-trivial to build an actual Monte Carlo that does both at the same time. So there is a deep formal mathematical connection, but putting them into practice in the same Monte Carlo is a way more complicated task.
Okay, thank you.
So by no means that is included in any pan scales investigation at the moment. So all this interest led to a lot of research in the past years since their discovery in 2001 by Dasgupta and Salam. And so a lot of applications are living log for different collider observables, both in the planar limit of large number of colors, as well as more recently in full color using discretization techniques. And in more recent years, there's been an explosion of new formulations with more modern QFT languages that aimed at extending this resummation beyond the leading log accuracy. However, the problem of resumming these observables to next to leading log remains actually a great technical challenge, and the first result at next to leading log is precisely obtained in the papers that I'll talk about today, and I'll try to discuss with you. So the goal of our work was to reformulate the problem in a new language, in certain approximations that I'll describe, in such a way that can be used to calculate numerically complex collider observables, different collider observables at once, and can be applied to different scattering processes, as we will see. So the first starting point is we, of course, cannot start from the most complex observable in the market. So we try to create a simple enough theoretical laboratory which reproduces all the conceptual aspects that we want to study and solve. So in this case, a typical, probably the simplest collider non-global observable is the cross-section for the production of a dijet system in plus A minus collisions. So it creates two stem and Weinberg jets with a cone defined with respect to the thrust axis. And we consider the rapidity gap in between the two jets and apply a veto in that region. What that means is that you can have any sort of emissions with any hardness inside the jets, but as soon as one partner goes inside this slice, this interjet gap, it gets vetoed. So we require its energy or transverse momentum, in this case, to be smaller than a certain threshold V. And to solve this problem, what we want to have is the fraction of events that survives the veto, the jet veto. And to solve that problem, we need to compute the precise distribution of gluons on the sphere at infinity as a function of the resolution scale of these gluons, that, for instance, is the energy or the transverse momentum with respect to the emitted system. And as we will see in a second, this problem becomes very soon very nonlinear. So it requires specific, engineering specific methods to be solved. So to describe what I mean, let me introduce a mathematical tool that you guys probably already know, given what Adam said. That is the generating functional method. This tool is very old, but very powerful, in my opinion, and is not widely used in Hadron Collider QCD calculations. And essentially, in a very heuristic way, what it says is that it gives an operational definition, an operational procedure to calculate the probability of having a final state with n partons, in this case, n soft gluons, besides the particles present in the bond configuration, in terms of an abstract object that is this generating function. So this probability is obtained as by applying the functional derivative on this quantity n times, and the functional derivative acts on the generating functional in this way. Generating functional is a functional of the energy scale, in this case, the transverse momentum of the soft gluons with respect to the emitting system, and a set of these probing functions that enter the definition of the functional derivative. The role of these probing functions is essentially to tag one emission as real. So when you act with the functional derivative on this object, that emission k of that corresponds to that probing function becomes a real emission as part of the n emission ensemble that you are generating with this algorithmic procedure. So this is quite nice for a number of reasons. First of all, it gives you a way to describe the problems in a way that is less dependent on the observable than most resummation techniques that tackle the observable by computing anomalous, observable dependent anomalous dimensions. While in this case, you can describe the whole evolution in terms of the relevant amplitudes in specific kinematic limits. The second reason why this is important, which will be crucial in this talk, is that it gives us a rigorous connection between the generating functional and an actual probability. That is something that I can simulate in a Monte Carlo algorithm. So that this allows me to solve complex problems numerically, even when analytical methods, as we will see, fail miserably. So to see how this works, let's consider the simpler case of a global resummation. So for instance, we compute, still stick to the case of plus and minus 2 jets, but we calculate an event shape, for instance, thrust, a leading log. So the leading log approximation is described by the emission of soft radiation of a bond configuration that is given by back-to-back QQ bar pair coming from the decay of a Z boson. And now, if you emit soft radiation of the system, of course, each new soft gluon increases the complexity of the color structure of the cross-section because it adds a color matrix to the whole problem. And therefore, you end up with a dramatically growing matrix that describes the color structure of this calculation. However, for global observables, one has specific azimuthal symmetries that allow us to integrate analytically over the azimuthal angle of the radiation with respect to the emitting legs, which results in the known property of angular ordering. So what that means is that the problem becomes much simpler, and the whole color structure becomes almost trivial in this case. So the generating functional, which is implicitly defined by its own evolution equation, will now describe the evolution of a quark square propagator that, with probability given by the delta, the Sudakov form factor, never emits in the perturbative realm, and it directly hadronizes. And with a probability that is proportional to the Eichmann factor, irradiates a gluon. And the radiation of that gluon that angular ordering asks us to be at an angle smaller than the angle of the between the quark and the anti-quark, will now create two additional generating functionals, one for the quark after the splitting and one for the gluon itself. Now, as a consequence of the same symmetries that I described before, one can make a further approximation and treat the gluon branchings perturbatively, so that a leading log, one can assume that the gluon never branches further. And therefore, you can think of the leading log calculation for this observable as a sequence of angular ordered gluon emissions of the quark lines. So this simple picture allows me to solve the integral equation for the generating function analytically in closed form and obtain this simple exponential form that allows you to do the analytic calculations for these observables, like the ones that are known in the literature up to high perturbative orders, but also to, as I said, to build a Monte Carlo procedure to generate this radiation, in terms of algorithmically, and then solve this problem numerically. So in general, a global observable is described by a paired system of this type of differential equation, one for a gluon jet, one for the quark jet, that can be applied to a variety of different problems and can be tailored to the observables at hand to simplify it further. Now, all of these simplifications fail for non-global logarithms, and there are two main obstacles that need to be solved, and they don't allow us to make these the approximations I've just discussed. The first one is color, and in particular, the non-global logarithms by definition don't have that angular symmetry that allowed me to introduce angular ordering in global observables, since by definition the observable acts differently at different angles. So it measures, for instance, a patch of phase space and ignores completely the rest of the phase space. So I cannot do any angular averaging. And therefore, one needs to keep track of the full color structure of the cross-section of the observable. And if you imagine writing an evolution equation that describes the evolution from a state with n partons to a state with n plus 1 partons, that last parton can be exchanged by any pair of legs in the n parton matrix element its conjugate, leading to, again, dramatic growth of the color structure. Mathematically, this means that one cannot write an evolution equation for the squared of the amplitude, but one has to write the evolution equation for the amplitude and its conjugate separately, and then evolve them, and then contracting them at the very end. So right now, we don't really have tools to do this very systematically, although some results exist at leading log with discretization methods, and some first steps are being taken in the Parton shower literature as well. Still, again, a leading log. So another solution that we take here is to take the planar limit of large number of colors, where essentially the exchange of gluons between legs that are not adjacent is simply suppressed by powers of 1c squared. So the whole problem of evolving the square amplitude boils down to calculating relative corrections, relative exchanges of soft radiation within a certain color dipole, and finding a way to iterate this to all orders in perturbation theory consistently. So the simplification is dramatic, and such that one can even write, crucially, the expression of the squared amplitude for the exchange of a soft gluon between a process with n external legs. And this is organized as a collection of color dipoles. So where we assign basically a color line to the quark, to any fermion, and two color lines to a gluon, and a color dipole is basically defined by one of these color lines that connects a pair of particles that are next to each other in the color chain. So this is a big simplification and makes a listed problem Markovian and on paper treatable. However, this is not the end of the story, and there is another problem to solve that has to do with the geometry of the problem. So this collection of color dipoles essentially means that things are very different from the global case that I described earlier. In particular, in that case, the basic element of the evolution was the square quark propagator. That was the generating functional was describing how this one evolved. Now I cannot do that anymore. And my basic building block is the dipole itself. So it's a color line that connects two particles. So if we write an evolution equation for that, it becomes very nonlinear already at the lowest perturbative order. We can see that easily. So we start from our QQ bar bone configuration that forms a color dipole. So one color line that connects, that goes through the fermion line. The generating functional describes now how this dipole entity evolves with the evolution scale. For instance, the transverse momentum of the radiation with respect to the dipole frame. So with probability given by a Sudakov, no emission probability, this dipole once again remains as such, never radiates anything, and it directly hadronizes. It with probability proportional to the soft iconal factor, this creates a new gluon with a transmomentum that is smaller of that of the initial hard scale. But crucially, and this is the main difference with respect to global observables, the emission of that gluons breaks the dipole into two adjacent dipoles. And there is a new color index, A, that enters the game. So we now have the dipole 1, 2 is split into a dipole 1A and a dipole A2. And each of these two generating functionals now evolves back with a similar evolution equation with updated indices. So basically you have to plug this evolution equation back into each of these two guys and carry on to generate a second gluon, then a third gluon, and so on. So the number of dipole grows quickly, and each of the dipoles then keeps evolving. Sorry, problem with Skype. Keeps evolving with the same evolution equation all the way down to low scales. Sorry, I need to switch off Skype because it's giving me some problem. Okay. Apologies for the interruption.
Do you mean that for a given observable, you have to calculate this generating functionals exclusively, depending on how many final states you have? Yeah, absolutely. So what it means exactly is that you cannot solve this equation analytically. So you cannot write an expression, closed expression for Z. And the best you can do, the only way we have today to solve this problem is to generate the generating functional with a Monte Carlo. So basically, you exploit now that operational procedural connection between the generating function and the probability of having a final state with n partons. And you write a Monte Carlo algorithm that essentially implements the evolution of the generating functional itself. So by doing that, then the solution of the Monte Carlo will be the solution to the evolution equation, essentially. And that is right now the only way we really have to approach the solution to a problem of this type, unless we take some linear limit in which things simplify, but it doesn't apply to the generic non-global problem. So the next step then to realize this equation is to formulate the problem in a way that the whole perturbation theory in a way that can be first of all allows us to resum these logarithms, but also allows us to extend and compute relative corrections that to extend the resummation to higher perturbative orders. So one convenient way to do this is to observe that, as I mentioned before, non-global observables by definition treat differently the radiation in different kinematical regions. So for the problem at hand, this means that inside the jets, the radiation is unvetoed and can be arbitrarily hard. So inside the jet, there can be an increasing number of hard prongs that create different new light-like directions that then are
seen by the soft radiation that evolves starting from these Born configurations. Conversely, outside of the jets, where the veto acts, the radiation must be soft and emitted at wide angles with respect to the emitting system. So the cross-section can be organized as a sum over the number of hard prongs inside the jets. That, as I said, the final number of reference like directions, that is what will be seen by the soft radiation that evolves starting from these kinematical configurations. So the first term is one has two legs inside the jet, so a QQ bar configuration. And this matching factor H describes the dynamics at high momentum scales that occurs inside the jet. And this is convoluted, which is an integral over the angles of these hard particles, with a soft factor S2 that essentially, starting from this QQ bar back-to-back configuration, adds an ensemble of soft radiation. Then in addition, the next term will be a term with three partons, hard partons in the jets with the emission of a hard gluon that is convoluted with a soft factor that now sees three different light directions, and so on and so forth. So the nice thing of this formulation is that there is a hierarchy between these different contributions. So in particular, leading log, one can only compute the first term, where the hard factor is calculated at leading order, and the soft factor is calculated following, it was evolved with the one loop evolution kernel. And next to leading log, which is what we aim for, we need to upgrade the perturbative order of the hard factor that is now computed at next to leading order, and the soft evolution, the soft factor evolves with the two-loop evolution kernel that I'll discuss later. In addition, we have the configuration with three legs, hard legs in the jets that pops up, where the hard factor is calculated at leading order, and the soft factor now once again evolves with a one-loop evolution, but starting from a configuration with three legs instead of two legs like in the first case. And excuse me, is it because in the soft evolution you require large NC that you can also require in the fixed order calculation, right? So in the end, you just factorize them to dipoles. Okay. Mm-hmm. Precisely. I'll come to that. So in fact, what you just said will allow us to simplify this S3 that will factorize into the product of two S2s for the two dipoles. And then you can do the same also in the hard coefficients, but what we decided to do is to retain the full color information in those two. But that is something that that one has the freedom to do. Mm-hmm. So to calculate this equation, I'll now discuss briefly the computation of the hard factors and then move on to the soft factors. So the hard factors, let's start from H3, is defined as a matching of the full cross section, as described by the soft factor here, that imagines that all the radiation inside and outside the cones is soft and full QCD. And this matching is necessary, of course, because inside the jets, the radiation can be arbitrarily far away from the soft limit, and therefore it has to be described by the full QCD Lagrangian. So at next to leading log, I need to compute this H3 at a leading order. That means that I take the calculation of the production of a QQ bar gluon inside the jet. So where I still require this gluon doesn't go in the interjet rapidity gap, because in there the radiation has to be exclusively soft. And I simply subtract the approximation where the gluon is soft. Now, since this hard factor describes the hard modes inside the jets, this computation can be treated at fixed order. So I can just expand this in alpha S and consider only the emission of a single gluon. The difference between these two pieces now is by definition finite in the soft limit, because I'm subtracting it off, but it still has a collinear singularity when the gluon is hard and collinear to the fermion line. And this collinear singularity crucially cancels against a collinear singularity that lives in the virtual corrections that I will include in H2. So the sum of terms, each term is individually divergent but the combination of the two is finite and physical. So if you approach the problem in dimensional regularization, everything is okay, and the poles cancel in the physical combination of the two configuration of 2 and 3 prongs. But we want to achieve a formulation in which this cancellation is manifest, and we take the 4-dimensional limits so that we can implement all of this construction into a computer. So what we do is we introduce a so-called subtraction procedure that is standard in fixed order calculations, where we subtract from each of these two configurations the same configuration, the same weight, but with kinematics projected into the 2-jet limit. So this combination of these pieces with their own subtraction counter terms gives a finite result in 4 dimensions, so it can be computed numerically. And now the integral of those counter terms that we introduced with an extra minus sign will be included in the H2, where it has the role to cancel the poles that emerge in the virtual corrections that are included there. So this is an extension to all perturbative orders of a well-known subtraction procedure that is called projection to bone. And the difference with respect to the original implementation is that now this projection also acts not only on the gluon that we generate, but also on the subsequent soft radiation that gets generated and addresses these events. Okay, so that means that, for instance, in the 3-jet event, the soft radiation starts from a 3-prong final state and radiates off that final state. In the counter event, where this configuration is projected back into the 2-jet final state, the two quarks will be back to back, and the shower will start from a 2-prong configuration to radiate. And so after this procedure, basically, was cancellation of singularities a little bit subtle, this contribution becomes finite and is computed numerically with a computer code. Then equivalently, H2 now describes the configuration with 2 legs, so QQ bar back to back, plus virtual corrections. And again, we subtract the soft limit to match it to the soft factor. And in addition, we put in the integral of the counter terms that we introduced in H3. And this cancels all the remaining single collinear singularity in this combination, and can be computed analytically, and actually gives a very compact formula in the end.
Pierre, so I think this is already a little bit complicated to understand right now at the moment, but can you explain me why this subtraction method is not just the simple dipole subtraction method?
You can use a dipole subtraction if you want, the standard Catani-Seymour subtraction. That would also work. The problem is, so here we chose a different subtraction method just because the subtraction is more effective in the sense that it reduces this 3-jet configuration to a very small region of phase space. But the crucial thing is that when let's take this first term, and you introduce a counter term let's assume the dipole method. In that counter term, the gluon has virtual kinematics, right? So it means that the event lives in a projected Born configuration that is the 2 jets. It doesn't see the recoil due to the third gluon. And that's where you compute the counter term. So, and that's simple to do in a fixed order calculation, but when it comes to this context, now this configuration, the event and the counter event, need to be addressed with a shower of soft radiation that is given by the soft factor is S3 that is convoluted with this. So the starting point of the shower in the first case is a configuration with 3 partners. So 3 light-like directions from which the soft shower starts. But in the counter event that lives in the 2-jet configuration, the shower will only see the 2 light-like directions and start from those. So the emitted gluon in the counter term is just a dummy object. It's not seen by the shower. It has to be so because that quantity has to live in the projected phase space. So this is a technical detail, but it becomes crucial to implement this in practice.
Okay, thank you.
So anyway, this was a technical parenthesis to calculate this hard coefficients H2 and H3. Now, once we have those, we go back to the formula of the cross section and tackle the soft factors. And in particular, one first problem, as Adam noticed, is that this soft factor S3 is in principle different from the soft factor S2 in that it sees a configuration with 3 different directions, while S2 sees only 2 directions from which starts the evolution. And this is actually already solved by taking the large NC limit, in that the 3-pronged configuration from which the soft factor S3 starts in large NC can be seen as a collection of 2 dipoles, contiguous dipoles formed by the quark and by the gluon in one of the quarks. And the 2 dipoles evolved incoherently from that point onwards. So basically, S3 can be seen as a product of 2 S2 factors, each of which is the direction of only of the particles belonging to that specific dipole. Okay, so that means that each of these S2 factors now evolves according to the evolution equation we described before. And I remind you that next to leading log, S3 evolves at with a 1-loop evolution kernel. That means that each of these 2 evolution factors, dipoles S13 and S23, essentially evolves according to the leading log BMS equation that we know how to implement in a Monte Carlo very efficiently since the original paper of Gavin and Rinaldi. A second problem, though, is, you remember, we also need to upgrade the evolution of the soft factor S2 that now needs to evolve according to the 2-loop evolution kernel. Okay, and if we start from the 1-loop evolution equation, the BMS equation that I introduced before, this is already rather complex, but if you compute the 2-loop corrections to this quantity, you end up with a way more complicated integral equation. And this is what we obtained earlier last year. I won't show you the terms here. I'll leave them for the backup. And of course, I'm happy to discuss the details. But the crucial thing is that this is broken into 3 pieces. As the names suggest, one piece includes the double virtual and real virtual corrections to the exchanges of radiation within the color dipole that we are correcting. Then one term encodes the double real correction, so the exchange of up to 2 soft gluons within the dipole. And eventually, we also subtract the iteration of the leading log kernel, so the BMS kernel, in order to iterate this equation correctly at all perturbative orders. Now, once again, these computations are done in dimensional regularization because there are divergences all over the place, and they only cancel at the level of the whole combination of the right-hand side. But what we want is also to write this in a way that we can take the limit for dimensions directly manifestly in the right-hand side at the integrand level, so that we can implement the solution to this equation in a computer program numerically. And to do that, we perform another subtraction that we introduce a counter term built on the kinematics of the 2 real gluons, such that when you subtract that from this last 2 terms, the final combination is completely finite. You can take the 4-dimensional limit, and then this can once again be integrated back into and combined with the virtuals to give once again a finite contribution. So after the subtraction procedure, the right-hand side is broken into 3 terms, which are individually finite in 4 dimensions. So I can take d equals 4 in at the level of the kernel, and I can aim at solving this equation in a computer numerically. Now, this is simple to, this is on paper, but practically the structure of this equation is too complicated. What this means is that this first term that involves real, virtual, and virtual corrections, as you can expect, has the same dipole structure of the one loop evolution kernel, because there's almost one real gluon that is emitted, the others are virtual. And that means that each dipole can break into two contiguous dipoles. So each generating function splits into two generating functions. And that's something that I can easily implement in a Monte Carlo algorithm using the Dasgupta-Salam algorithm or a properly modified version of it. However, the second term that enters the evolution equation is way more complicated, and it involves what we call tripole configurations, in which a dipole can split by emitting two gluons and now evolves into a three-dipole system. And this iteration is something that for now we don't have any methods to implement efficiently in a Monte Carlo algorithm. And so we need to find, although it's a very interesting problem, a way around it. And what we do is we devise a perturbative solution to this equation that works as follows. So we write the generating function of z that solves that equation as the sum of two terms, z0 and z1. Z0 is the solution to the evolution equation with only the first term. And I remind you that this first term has the same structure as the leading log evolution equation. So I know exactly how to solve this equation numerically exactly, so in exact form. Then I plug back these two equations into the original evolution equation, and I can neglect terms that are quadratic in Z1. That's because they are of next to leading log order or higher. That means that formally, in perturbation theory, I can throw them away. And I can then linearize the equation Z1. And the picture that emerges is actually quite elegant and simple. So if we think of the evolution tree, so we start from the center of mass energy of the QQ bar pair, and we evolve down to the cutoff scale of the order of lambda QCD. What we have is a sequence of steps where we iterate the kernel Z0. And we have a single insertion of the kernel Z1 that can occur at any scale in the evolution tree. Okay, so at any scale means that this scale has to be integrated over effectively during the evolution. And when the Z1 insertion occurs, this can create the one dipole that is splitting, represented by the branch of this tree, can create three additional dipoles. And then from that point onwards, you carry on evolving again with the initial evolution equation that can be solved once again exactly. So this is a complicated procedure, but it can be implemented exactly and precisely with technology inspired by so-called truncated showers that we developed precisely to solve this Monte Carlo problem. So
I might have a question about this. So I'm not familiar with the truncated shower itself, but we are working on a Parton shower. So we are working mostly with jet quenching now. And so what we are doing is that when the Parton scatters on the medium, that the scattering is going to induce you additional emissions to vacuum, like more emissions than the normal QCD Brechstangen. And what you can have there, then you can have the emissions which you have to resum. You will have, because they have soft divergence. And you will also get emissions which doesn't have soft divergence, or they have a slightly so less strong divergence. So yes, we try to write an evolution equation, or like the similar what you have, and in that case you can imagine that you have the generating function, and the generating function can generate two processes. One of them gives you the ones which are very divergent and another one which is less divergent. And what you would like to do is, of course, you want to resum the one which is very divergent, and then you would like to do some expansion in the one which is less divergent, right. Very similar to the thing what you did here. And yep. The thing what we were, so for us, it was a bit more clear in the sense that we have time-ordered perturbation theory, and we try to imagine that what is the beginning of the shower and what is the end of the shower. But when you do these truncations, then you can get into the problem that do you include, so can you have, this fixed order correction? Can it happen in the beginning of your shower, or will your generating functional truncation only let it in the end?
It can happen anywhere in the shower.
Yeah,
that is essential to be correct.
Exactly, and I'm curious that so based on what you just showed, if you truncate your shower at a given point, then that can only let you corrections only in the beginning or only in the end. And I was
no, but you carry on. So I call it truncated, but it carries on. So what we do in practice is the following. So before we start the evolution, let's say we're up here at S, we generate the scale kappa. That is a scale, for instance, uniformly distributed between S and lambda QCD squared. Then you run the shower using this evolution equation up here on the right, but that shower doesn't have Q naught or lambda as a cutoff, it has kappa. So the shower is interrupted at kappa. Now, at kappa, that is the scale of the insertion, you generate the insertion. So you pick one dipole, and you, with a weight given by that of the insertion, you split it into 3, for instance, and now update the color structure, the dipole structure due to this new splitting, and then you end up with a configuration with n plus 2 dipoles. And now from that scale on, you carry on evolving with the original evolution equation all the way down to lambda QCD. So the shower is not interrupted. What it means is that if Z1 is 0, or the insertion is 1, this truncation procedure is absolutely identical to the full shower run from beginning to end. Okay, so it's just a way to insert a perturbation of the shower evolution, but it's really a 1 plus alpha S correction of the shower evolution. So if the weight of that alpha S correction is 0, then the shower history is unchanged. So you're not truncating it effectively, you're just interrupting it, inserting, and then you carry on down to low scales.
Right. The way how I imagine this is that usually when you write the evolution equation, then you can write it either in the forward evolution way or in the backward evolution way. So do you have a splitting and then 2 generating functional, or 1 generating functional and then a splitting? Like you can formulate this in both ways. They are equivalent. And what you are doing here is you just iterate the evolution equation 2 times, and you say that you truncate the one in the middle. Maybe this is a bit.
Yeah, I'm not sure I understand this this latest point, but yeah, maybe, we can discuss it later, perhaps with.
Yeah, but this is very interesting. We were actually having, we were thinking of the very similar things.
So this is not entirely new. I mean, we use this to solve well, we didn't formulate in terms of generating functions, but to solve the resummation for global observables in a similar way. But in that case, it's so simple that you can work it out analytically, essentially. You don't need a Monte Carlo really to do the thing. Mm-hmm. But it really amounts to inserting this special block at any kinematical point in the evolution history. This is really what the one has to be. And you have to be careful that insertion doesn't break the leading laws, right? That is crucial. So if you set the weight of that insertion to 0, virtually it has to reproduce exactly the original result.
Right. Right. And is
This
it
is a check that we perform numerically.
and is it possible to insert this block just in the beginning, like similar the way how you would match a normal particle shower with a fixed order matrix element?
So it is possible to do it, but it wouldn't be accurate at this logarithmic accuracy. So you cannot claim in this context next to the in log if, for instance, the first, this block Z1 only corrects the first two emissions of the evolution. That wouldn't be accurate logarithmically.
Okay.
You correct the shower at fixed order. That means that up to alpha squared, you are correct. But then starting at alpha cubed, you're wrong.
I see. Okay, thank you.
Sure. Okay, so let me rush a little bit. So, okay, this is a complicated algorithmic construction, and sorry for being a little technical here, but so one crucial point here is to understand if you're right and we do things correctly. So we do a number of checks like the one I just mentioned. We also write two completely different codes and make sure the results are identical. But one peculiar test that is important is to expand a result to order alpha squared and compare it to a fixed order QCD calculation obtained, for instance, for this process with the code event 2 that is public. So what we calculate is the differential distribution of our cross section with respect to the log of the observable, the large quantity, and subtract from the event 2 prediction our expansion. What we expect is if the next to leading logs are correctly computed, the limit of L going to infinity. So when the log becomes very large, this difference has to go to 0. And here I show in these two plots this difference computed for two different observables, the transverse energy in the slice and the energy in the slice for different jet cone sizes in three colors. And we see that in all cases, the difference does indeed go to 0 within statistical uncertainty for large values of the log. This gives us confidence that what we're doing is indeed correct. We then can resum these non-global logs and look at the final physical resum results. This plot shows the cumulative distribution for the transverse energy in this interjet repeated slice for cone jets with cos theta, where theta is the opening angle of 0.9. So these are relatively narrow jets. In blue, I show the leading log prediction with theoretical uncertainties, and in orange, the next leading log prediction. And we see that in the lower panel that the next leading log corrections are rather sizable numerically. They can reach up to about 40% before we hit non-perturbative scales. And the theoretical uncertainty is reduced dramatically by over a factor of 2. So this gives a very promising perspectives for the application of this type of computation to collider phenomenology. It is also important to look at a breakdown of this next to leading log corrections. So this plot shows the ratio of the different contributions to the next to leading log cross section to the leading log cross section. And these are the piece with 2 prongs, the evolution of the zeta naught generating functional. This is the piece that we calculate exactly at all orders. And this is the orange piece, and by far numerically the dominant piece. The second piece in blue is the contribution of the insertion of Z1. Remember, perturbatively, we expect this quantity to be much smaller than Z0, so that we justify not only formally, but also numerically our perturbative treatment of this evolution equation. And we see indeed that for this narrow jet configuration, these effects are rather mild. So ensuring that Z-squared terms that we are neglecting, which are of higher order nature in our counting, are also numerically quite contained, and they are under control within these uncertainty bands that we quote. Finally, we have the piece with the 3 partners in the slice in green that is also moderate, but can become relevant within the uncertainties we quote in certain kinematic regimes. So here is also the result for now fat jets with the cosine of the opening angle of 0.2. And the qualitative statement about the size of next leading log corrections, as well as the reduction of the uncertainty bands, are about the same. And in this case, if we look at the breakdown, the impact of the Z1 correction is even smaller. So justifying even further in this case, jet case, the perturbative solution to the evolution equation that we devised.
And
so,
what happens with the cumulative distribution at the small arguments? So why does it go above 1?
Right. So this has to do with the fact that I'm defining the cumulative distribution by dividing by the Born cross-section. So this is really the cross-section for E plus E minus 2 QQ bar. And when remember the cross-section for next to leading log has an H2 and an H3. They now are calculated at NLO. So when you integrate inclusively over the observable, the two soft factors S2 and S3 essentially integrate to 1, but H2 and H3 amount to the NLO cross-section for a gluon outside the slice. So there is a next to leading order K factor that is applied in the limit where the slice is basically not constrained, and that comes from the hard factors.
Mm-hmm.
So basically the two curves have a different normalization. Here I'm just normalizing to the same thing to have a honest comparison between the two. But if I had to define the unit normalized cumulant for the next to leading log, I will need to normalize by the next to leading order cross section here, not the board.
And that doesn't depend on, does that depend on the square root of S divided by the transverse energy?
No. It depends on root S through the coupling, but not on the observable. So it's completely independent on the observable. It depends on the size of the slice. So this cos theta jet.
Mm-hmm.
You can see it, for instance, from here. This is basically the normalization that I'm talking about. It's a function of C that is cos theta jet.
Mm-hmm. Yeah.
So, okay, so this is for us very cute, but of course, I mean, E plus E minus to jets is an interesting problem, but doesn't have a very practical relevance right now. So we want to eventually apply it to PP and LHC. And of course, here one moves to hadron collisions, and there are a number of things that get more complicated there. In particular, we know there are additional sources of non-global corrections that come, for instance, from the exchange of Glauber gluons between the initial state particles in a hadron scattering. But and these give rise to superleading logarithms, and they are not very well understood, just to be a euphemism, but people are starting to actually understand them in more detail just now. But the crucial thing is that all of these effects are subleading entities. So if we stick to the planar limit that we formulate things in, all of these effects are irrelevant, and we can directly apply our algorithmic procedure to an LHC observable on paper, and that will be accurate in the planar limit. Of course, the implementation aspects are a little more substantial in that case. There are a number of very interesting problems at the LHC that one can solve. One is, of course, the calculation shown here on the right of the survival probability of gluon fusion initiated Higgs boson production in association with two jets when one applies VBF, vector boson fusion cuts. And this is crucial background for the VBF measurements at the LHC experiments. And it's a quantity that needs to be estimated very precisely. Now it's becoming a real bottleneck to extract accurately the Higgs boson couplets. And this study by Hatta and Ueda that I showed here on the right, that is done on leading log, they also show the comparison to the full color approximation. This is one of the color channels. And as you can see from the plot, the subleading color effects are actually, besides being, of course, incomplete due to the existence of these Glauber modes, they are extremely tiny or almost invisible. So at the moment, to be honest, I haven't seen directly a case where these subleading color effects become numerically relevant at all orders. So in first approximation, they can be safely ignored. Other applications are, of course, the study of jets, so jet mass or substructure observables, as well as, for instance, study of jets configurations with jets with large rapidity separation with a veto in between that are used to look for the FKL effects at the LHC. But given the currently poor description of Monte Carlos and theoretical calculations, it's very difficult to assess whether the discrepancy with data is actually a sign and evidence of the FKL effects or just due to a mistreatment of the QCD prediction. So secondly, and lastly, these things will be relevant in the construction of higher order Parton showers, for which these theoretical developments will provide some guidance. And the number of problems here, there are still a number of problems, but what I've presented, a list that allows us to define them very concretely and very clearly, and it really gives us a roadmap towards what should be done to realize this kind of computation in the context of a shower Monte Carlo. So in particular, one has the first problem is that we cannot think of use the perturbative solution of the evolution equation anymore, since the shower we need to preserve the self-similar structure of the evolution, and we need to find a way to iterate the Z1 quantity at all perturbative orders. And other perhaps less relevant problems still important become the use of momentum conservation in a shower Monte Carlo that's not present in every some calculation like the one I presented, and that needs to be incorporated consistently in this iteration. That is also a very subtle point. So concluding, I presented the formulation of a new formalism for the calculation of non-global observables and next leading log in the largest limit. This is formulated in terms of soft generative functionals that are the evolution equation is solved in terms of a Monte Carlo algorithm. And this allowed us to obtain the first next leading log resummation for final state radiation in a plus C minus, where we find that non-global corrections are indeed substantial at next leading log at the 40% level. And the inclusion of these corrections leads to a considerable reduction of theoretical uncertainty. Now, looking forward, we would like to apply this technology to PP collisions, where the planar approximation allows us to apply exactly the same algorithm in that context, avoiding complications that arise in general when one considers partons in the initial state. So this again remains algorithmic, but of course the implementation work is a little more important, and this is left for future work. We will address it soon. Also, an important conclusion is that having a theoretical description of next leading log and global correction will provide a roadmap towards the implementation of this type of relative corrections in the context of Parton shower algorithms, and therefore will give us, and it is an important insight on how to formulate a new generation of these tools in envisioning higher precision in this type of simulations. Thanks very much.
Yeah, thank you very much for this very nice presentation. Yeah, it definitely gives us a lot of insights in the work that you made here. I will